All right, everybody, sorry to keep you waiting. Whoa, it got real close, didn't it? And top of my head, all that good stuff. This is not the question we'll be doing right now. I'm on the wrong page. I'm on the wrong document. There we go. Uh-oh. All right, that will be our last question we do. This will be video 2. Video 1, back. 1, 2. This is fall 21 T1 part 4. And here we are. And we're going to get busy. Here we are. We got a big old molecule. You're hoping for an even bigger molecule. The bigger it is, the more easy points you get. I need you, and I'm going to have the chats open because I'm not going to have it open. I need you to have the table in front of you where we have the ppms here. And when I make a mistake, because I'm just going to go from memory, I don't want to keep alternating back and forth. When I make a mistake, I want a comment. I hope I don't make a mistake. All right, so there's a lot going on here. We want to do the easy part first, the number of H's. Now, in this molecule, you'll see there's a lot of H's that never got labeled. There's only one reason this would ever happen on this question. Symmetry. Look at this CH2 right here. The same CH2s here. How do I know? Go CH2, CH2, NH. CH2, CH2, NH. Carbonyl, CH with an O. See, a carbonyl, CH with an O. Do I need to go on? This matches this. And this matches this. So remember to double things when they need to be doubled because they appear twice in the same molecule. There are 4 of these, 2 of them here, 2 of them here. I got a note here that says participants can now see my screen. I hope you could see it before.
Yeah, we could.
Sorry, you could? Thank you. We have a CH2 and a CH2, and we're going to go with green. We got 4 of those. Same for M. Wait, N and M. I'm starting at M and N, dude. Sorry. N and M are 4 each. You got to go in the right place at the table, right? M and N are 4 each. L, the H on the N. There's 1 there and 1 to the right. That's 2. O, let's see, L. D. Let's go with D. There's 1 here and 1 way over here. Right there, that's 2. And that was L. You got L. D, there's 2. Weird not having these things really in order. They're in order for a while here. E, there's 4. F, there's 4. G, there's 4. H, there's 2. I, there's 2. J, there's 4. There's 2 here. And J is also here. 2 more. That's 4. J, 4. K, there's 4. Where's this A and B? All right, A, there's 2. B, there's 4. C, there's 4. O and P are on the ring. O, there's 1 H here. And if you're looking symmetry, there's another one right there. This is O. There's 2 of them. And 2 P's. Okay. Nice. Want to do multiplicity next? Why not? You got to look at your neighbors, add 1, and you'll get a number. Convert the number to one of these words. They're in order. Okay, O. Listen carefully. You don't have neighbors if you're attached to any atom other than carbon. And it's a reciprocal non-neighbor relationship. H is not a neighbor to B, and B is not a neighbor to A. Oxygen doesn't let these H's talk to each other to create patterns. Okay? So, that's a fact you might not know, and you just learned it. So A is, for an alcohol, is always a singlet. And if you look at the table, it should say broad singlet. If it doesn't, I'm telling you, and you need to know it, alcohols have broad singlets. A, singlet. B, it has neighbors, but they're not called A. These are neighbors. These are not, because that's not a carbon. So 2 neighbors plus 1 is triplet. C, 2 neighbors called B plus 1 is triplet. D, no neighbors here, clearly no neighbors there. 2 neighbors here. D is another triplet. What, triplets? E, 1 neighbor upstairs, 2 more downstairs. Total 3. 3 plus 1, quartet for D. E. F, 2 neighbors upstairs, 2 neighbors downstairs. 4 plus 1, pentet. G, 2 neighbors called F, 1 more called H. That's a total of 3 plus 1 is Q. Quartet. There's G. H, 1 neighbor here, 2 more to the left. That's 3 total plus 1, also a Q. I, 2 neighbors on top, 1 neighbor below. A lot of Q's in a row here. That's just coincidence, ladies and gentlemen. 3 neighbors gives quartet for H. Wait, we just did H. I had 3 neighbors, 2 here, 1 there. 3 plus 1 quartet again. J, 2 neighbors up top, 1 more below. There's a quartet spree going on here. K, just 2 neighbors plus 1 triplet. L, where are you, L? Oh, what I said about oxygen also holds for nitrogen. If you are H bonded to an N, you have no neighbors. You are not neighbors to anybody else. So singlet, broad. I'm telling you now, if you're H bonded to N or H bonded to O, you're singlet and you're broad. I'm not going to grade how you draw broad, but broad just means it's not a sharp peak. It's a wide peak, wide. Hydrogen bonding is Y if you're curious, but don't worry about that. M, H is not a neighbor down here. No. These 2 are neighbors though. We have a triplet combination coming up, MN. N does not have a neighbor underneath. It has 2 to the left. That's 2. 2 plus 1, triplet. O, no neighbors up here. 1 neighbor down there. So first doublet. P, tricky story here. These P's are identical. They're twins. If your twin lives next door, it's not considered a neighbor. I have no better explanation. If your neighbor is identical to you, like your clone, Ignore it. It's not a neighbor. It's you. You just happen to live next door. It's a weird little universe. Okay. So don't count a neighbor that's identical. I know it's a new thing again. They keep showing up, right? We're running out of new things, by the way. Okay. So P has the neighbor up here because that's not identical to that. They're different distances away from this, which makes them different. Okay, so P has a neighbor called O. Same for this P, that neighbor is called O, but you only look at one of the P's. One neighbor plus one is doublet. If there was no symmetry here, if this was a different C, like say there was a group over here, like a group, then that would change everything in this molecule. If there's a group that was here but not here, then these guys would be neighbors. They would have different labels, etc., etc. Okay. Now the ppm stuff. Okay. Alcohols. It is my belief that the table says an H attached to an O is somewhere between 0.5 and 5. That might not be exact, but it'll be exact enough. I'm going to put a peak at about 3, which is somewhere in the middle of that range. It's got a very wide range. Why? Hydrogen bonding. Another reason hydrogen bonding has an influence. So I'm going to go 3 ppm. Subject to change if I have another 3 ppm showing up. B. H attached to a C that is an alcohol. Should I get the exam? I have the exam open. It's not a big deal. H attached to C that is the alcohol. Here's the exam. Here's our table. There's the picture version. H attached to a C that is an alcohol. Anywhere between 3.4 and 4. How about 3.6? Sound good? Somewhere in there. 3.6. That's a 3. C, alpha to a carbonyl. Alpha to a carbonyl. How about 2.4? How about that? D, also alpha to a carbonyl, but also part of an ester. Big asterisk for D. It's in 2 categories. Baseline. If you don't know what this means, you missed last lecture. Baseline, R3CH. R3CH, carbon with 3 groups on it. Nothing special on any of these R's. 1.4 to 1.7, we're going to call it 1.5. Baseline, 1.5. I'm not going to draw things. Alpha, it's also an alpha H on an alpha. We're talking about D. It's alpha to a carbonyl. 2.2 to 2.4. We just did alpha to a carbonyl right here. That would jump it up to 2.2, no, 2.3 or 4. We wrote it down, 2.4. It's also, D is also a C that's part of an ester. Okay, so I need to look up that. Part of ester. I don't even know what to write. I'm going to write the word ester. It's an H attached to a C attached to an O in an ester. You agree? H, sorry, round D. H attached to a C attached to an O. That's an ester. Find it. H attached to C attached to an O. That's an ester. H attached to C attached to an O. We're over here, people. 4.3 is the middle of that ish. So that jumps to 4.3. Your two jumps. Yes, you're going to have at least one H in the two category option. And it's we're doing a lot of work for a third of a point, but you know, really shows who understands their stuff. That's plus 2.9 here. I'll put it in black. What do you do to get from 1.5 to 4.3? You add 2.9. What do you do to get to 1.5 to 2.4? You add 0.9. Combined, you add 3.8. 1.5 plus 3.8 will be your prediction. 1.5. That's a terrible 5. 3.8 equals 5.3. Ah. 5.3. E. E is just RCH2R. This is not part of the ester. It's a carbon, it has carbons on each side. RCH2R coming up. Third item. 1.3. Coming back. Purple. We don't have a 1.3. If I get matching numbers here, I'm going to adjust the two matching numbers so they're still in their categories, yet different numbers. F. F. Same as E. It just happened. Remember, the range is 1.2 to 1.4. I'm going to say that an H that's RCH2R closer to an O is going to be higher than an H RCH2R that doesn't have an O the same distance. This just became 1.4, which is the top end of the range. Still in the range. I didn't really change anything. And the bottom end of the range. F. Please don't try to tell me G is also RCH2R. You have ignored the fact that it's also allylic. One away from an alkene. Okay? All right. So, G, allylic. Find it. Allylic. It's even written for you. My goodness. H attached to a C attached to an alkene is allylic is 1.6 to 2.6. The middle is like 2.1. 2.1. H is internal vinyl. Means it's attached to the alkene. That's vinyl. Internal means it's in the ene is in the middle of a chain. Keeping in mind H and I are both in the same category. I'm going to use the low end of the category for this and the high end of the category for an H closer to a fluorine, the most electronegative atom known to man. So low end of the internal vinyl, high end of the internal vinyl. Let's find the internal vinyl. H directly attached to an alkene. Terminal, which means end of a chain, versus internal, middle of a chain. Low end, 5. High end, 5.7. I got a good range in there. I'm going to go low end 5.1, high end 5.6, so it's not at the end. I will not grade you as long as you're low end for one, high end for the other. You could even put them with the exact same number as long as I can clearly see their different peaks. You're fine. 5.1 for the fluorine, or closer to fluorine, 5.6 for the other one. 5.1 closer to fluorine, which is I. 4.7 for the one that's not as close to fluorine. J, allylic also, but closer to the fluorine, very close to a fluorine. So 1.6 to 2.6 for allylic. We already found that. I'm going to go 2.5. I don't have a 2. I have a 2.4. I'm going to go all the way to the 2.6 then, just to stay a little bit away from there. 2.6. high end of the allylic range. K, RCH2F. RCH2F, 4.4 is what I'm going to give it. Please don't add a decimal. I never need a second decimal. 4.4. Here. L, H attached to N. That's all you're going to find on this chart. Oh, I see my chart down here. I could have been doing this all along. Look at me. H attached to N. So I was wrong with the alcohols, wasn't I? Let's see. Alcohols were a little wider, but we're still there. Good. Pick something between 0.5 and 5 that you haven't used yet. That's all I'm going to say. 0.5 and 5, haven't used it yet. Don't go as low as 0.5. How about 1.8? There's nothing at 1.8. Once again, if you're in the range of 0.5 to 5, you're okay for L. L. M, H attached to a C with a nitrogen there. I don't know if we're going to find that. We're going to give it a shot. H attached to C attached to nitrogen. I don't know if that's on here. It is. My apologies. I found it right here. H attached to a C that's got an N. The number of H's is not the big deal, is it? The N is the big deal. So how about 3.5 if we haven't used it yet? 3.5 if we haven't used it yet. We're talking about M. We're talking about H attached to C attached to N. 3.5 if we haven't used, we use the 3.6. Let's go down to 3.4. That's the low end. Stay away from that 3.6 a little bit. Getting there, guys. N. N is a C, H on a C that's attached to phenyl. We call that benzylic. B-E-N. Find benzylic. Whoa. I don't know what happened there. Oh, activity 8. That's the one we didn't do earlier. Hello, please go away. And why does my PDF not, my PDF close? There it is. I don't even know what I'm looking for. Benzylic. H attached to C attached to phenyl. Methyl, a little lower than not methyl. This is a closer version than this one in our example. I'm going to go 2.5 if it's already not taken. 2.4 is taken. Yeah. 2.6 is taken. It's going to be a little tight, but we got to use 2.5. Oh, remember, ICH on benzene, the number in my mind is always 7.1. I don't care what this table says. 7.1 is closer to real benzene than the middle of this, which would be 7.5. I'd rather see 7.1, people. Once again, I'll cut you slack, but I get happy when I see students use 7.1 for normal benzene. Try to make me happy. We've got nothing special on either one of these, so they're both going to be close to 7.1. I wouldn't call a carbon group very special, would you? And so that's not special. Nothing electronegative there, nothing electronegative here. I'm going to call one of them 7.1 and the other 7.2, and I wouldn't even grade you which is which. You pick, flip flop, 7.1 for O, 7.2 for P, or vice versa. Vice versa if you're speaking Latin. All right. Versa. Sorry. Okay, we're gonna do C, and that'll be the end of this segment. And I actually changed my mind on what's gonna happen here. I'm going to let you do this on your own. I've got a very pretty picture. It took me a long time to make for the key, by hand and a ruler, and I'm not going to do it using this thing here. And you're going to talk to me if you still need help drawing the spectrum, because what you're doing is making this into a picture. Okay, that's all you're doing for B. There's only one picture that matches all this data. Okay. C is a weird question. How many signals would be in the proton decoupled C13 spectrum? Do you want me to translate? Do you want me to write my translation down? Translation, C. Translation. How many types of carbon are in the molecule? That's all you need to know about C13 NMR spectra. There are people that have devoted their lives to C13 spectra, and there's a lot more you can do with it. There's a lot more you can do with NMR spectra, proton NMR spectra too. There's an amazing field. Types, I wanted to be all caps. Remember, if there's symmetry, then you have to account for that. Hello, thank you. There's my C translation right there. Yeah, I think we can read it. Can I use red dots for types of, no, not red dots. I'm gonna have to use circles. Here's what I want to do, folks. Just had a little brain, what do you call it? Epiphany. I'm gonna copy my molecule again. End of this exam, second last page. I'm gonna copy it with my Snippy. Where are you, Snip? Snippy disappeared on me. Here you go. Oh, Snippy gives me a hard time. Here we go. I just need my molecule. Here, copy. Bring them on over. Blow them up. Erase the extraneous. Big eraser. Oh, big eraser is dangerous. I'm going to circle types of carbon. I'll start here. It's gonna look pretty like a bad artist when we're done. I hope you agree this carbon is identical to this carbon. So that's one type of carbon. Another type of carbon. You don't have to do circles on your test, everybody. Another type of carbon. Whoa, I don't want my circles crossed. And another type of carbon. So far, we got 4 types of carbon. See how this is going? It's actually from my perspective, it's kind of entertaining. I know, I'm easily amused. There we go.
Professor, how are they different carbons if they're identical?
That's a non-question. If they're identical, they are not different carbons. They are not different types of carbons if they're identical. So maybe I misheard you. Restate your question.
Oh, you said those are different types of carbon.
Each circle is one type of carbon.
But aren't they identical? Oh, I see what you're doing. Okay.
Why that's one type of carbon and not 2.
Okay.
Okay, here we go. There's another type of carbon. And orange. I think my entertainment might be ending soon. You know, sometimes entertainment becomes work. There you go. I think, can I just do this from now on? If I use a unique color, I'm running out of colors. I got gray. I never use gray. I think I do. At least I can do this one. That's the CH2. Yeah. Back to pink. There we go. Carbonyl. Can I just use arrows from now on? How about that is the same as that? I think you got the idea, right? So we're counting arrows or circles. Carbonyl. Oh, he's green again. That's okay. Ends don't count. These are for carbons. Yeah. How about D straight across? I can't go close. Uh-oh. Oh, I already did D. What am I doing? Okay. Where am I? CH2 is here. That one's an easy one. And so is this one. This is a lot of work for a point, isn't it? It is just 1 point, I think. Yeah. These two are hello. And these two identical. Right here. These two carbons are identical. And these two carbons are identical. And these two carbons are identical. Count circles and arrows. This is where it gets fun. I go from the bottom here. Counting circles and arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I haven't done any of the arrows yet, have I? 15,
No.
16, 17. Does the key say 17? I hope.
It's time consuming. It should be more than one point because it's so time consuming.
I know. Maybe I should fix that, huh? Maybe make it 3?
No, leave it 1 point and we'll just go to the more important ones.
There you go. Either you both have good arguments. Okay. I said 17. Let's put it in our key here. Where's our key? We're on our key. Whoa, dude, don't do that.
Yeah, it's 17. It's 17.
Yay, thank you. Yeah, let's do something cool here. All that work, is there something special? How about I like that. There you go. And then D is review. When now it's not always clear what I want here, but if you look at every answer key, this is all about the formula. Okay. So isn't every carbon part of symmetry in this molecule? There's not a single carbon that wasn't part of symmetry. So, hey, can you tell me how many carbons are in this molecule, please? If there are 17 types of carbon and there's duplicates of each carbon, how many
34.
carbons are in the formula?
34.
Yes, C34. Ladies and gentlemen, if you want to know the number of H's in this molecule, I'm starting here, running tally. You ready? 2, 6, 10, 12, 24, 26, 28, 32, 36, 38, 42, 46, 48, 50. How many nitrogens? 2. How many oxygens? A lot. I don't really care about the oxygens, right? 1, 2, 3, 4 times 2. Is that right? You got to correct that formula for me. That's what my symbol for correcting the formula is. It's a non-official symbol. C34H48. Why did I do that? When there's nitrogen in the formula, it brings an extra H with it. To get rid of the nitrogen, you got to take the H off. Now, what's this? The normal C34 that has no rings, no pi. C34, what's 2 times 34? 68. What's 2 plus 68? 70. Subtract 70 minus 48, you get 22. Divided by 2, because it's pairs of hydrogens we're talking about. Check your work. Your molecule needs a total of 11 pi bonds and rings. I'm going to count and then multiply. Yeah, the appendage here, I'm going to count and multiply by 2. Because there's 2 of those. 1 pi, 2 pi, 3 pi. So 6 pi's on the appendage. Appendages. 1, 2, 3. And then 7, 8, 9, right? For these pi's. And then a ring is 10. And how come I got 11 in my answer? I did something wrong. I don't want to waste more time though.
You did something wrong on the answer key. You left it C34H50 instead of C34H48. So you're right here, but the answer key is wrong.
Oh, I forgot to account for the nitrogens is probably what happened, right?
Yeah, you didn't do that. You did that here.
Oh, well, I'm glad this came up. So we're good here, but I still haven't accounted for an IHD of 11. That's still my problem, right?
Yeah.
1, 2, 3. I'm just gonna count all of them. 3, 4, 5, 6, 7, 8, 9. I got 9. I don't know what I'm doing. I'm tired.
Ring.
I got 1 ring, right? 1 ring, 1 pi. So an IHD of 4 for a benzene, right? It's got 3 pi's in 1 ring. 4, 5, 6, 7, 8, 9, 10. I'm back to 10 at least. Did I miss? Maybe I misadded my hydrogen. I think I did. Start from the bottom. 2, 4, 8, 12, 14, 18, 22, 24, 26, 30, 38, 40, 8, 50. Didn't miscount. Oh, there's fluorines, ladies and gentlemen. There's fluorines. Ah! I forgot the fluorines. They're here and here. There's 2 of them. Beautiful. Beautiful. The key is 100% correct. Oh, they're supposed to go alphabetical, aren't they? Oh, boy. F2. F2N2. How many O's were there? 8? That didn't change. I don't want it wrong. So 1, 2, 3, 4. Corrects to 50 because you lost 2 for the nitrogens, you got them back for the fluorines. Right? Smaller eraser. Remember halogens? What do we have? It's 50 down there. 20 divided by 2. 10. Oh. There you go. So the easy way to remember what to do with elements other than carbon and hydrogen is the periodic table. Make your oxygen into a 0. Periodic table. What's to the left of oxygen? Nitrogen. What's to the right? Halogens. Good for the whole column. 0 is a 0. You're gonna add an H for every fluorine you got. You're gonna subtract an H for every nitrogen you got. You're gonna do nothing for oxygen. That's how I remember it. That's a wicked video. That took 50 minutes, no, 40. Okay, I'm not gonna do the picture. I am going to do the next one in the next video, which is the big one.
Are you gonna sketch
Oh.
it?
I'm not gonna sketch it. I've got a beautiful sketch in the answer key already, and it would be a waste of our time to watch me make that again.
Okay.
That's all I'm saying.
Yeah, no problem.
I may have shifted some of the peaks around, but that's all that would be different. They didn't shift very much, I'm telling you. All right, so I'm gonna stop this share, and then I am gonna start our next one with this. All right, I'll be back.
Thank you.
You're welcome.